we have studied in our previous classes. Okay, so let's start what we have studied in our previous class and why we are going to read the topic, the shapes of atomic orbitals. Okay, so let's start. How do we need to study this particular topic? But before going to this topic, see what we have studied in our previous classes. In our previous classes, we have completed all the atomic models. Either it was Bohr's atomic model, Rutherford's model, or quantum mechanical model. Okay. Besides this, we have studied the quantum numbers, which are super important topic, which gives us brief discussion, which gives us brief idea about how can we put our orbitals in a particular way. Like we can name the R orbitals like 1s, or it is 4p, or it is 5d, and so on. Okay, so all these terms were classified on the basis of quantum numbers. This whole concept we have studied. Now today we're going to study with the new topic, that is the shapes of atomic orbitals. Okay, before going to shapes of atomic orbitals, I have already told you about psi and psi square. In the quantum mechanical model, we have studied what is psi, and we have studied what is the physical significance of psi square. I have told you that psi doesn't have any kind of physical significance. It is just a representation, a mathematical representation, I should say, a mathematical representation of wave function. Okay, this was something we have studied in our quantum mechanical model. In quantum mechanical model, we have studied that psi represents actually the mathematical representation of wave function, whereas the psi square has actually the physical significance. The psi square basically gives us the probability of finding an electron in an orbit. I'm saying in an orbit, not an orbiter. Okay, so the probability of finding an electron in an orbit, it can be easily calculated with the help of psi square. Okay, this was all we have studied. Now, on the basis of this, we need to discuss what are the shapes of atomic orbitals. I'm talking about orbitals right here. And you know very well that we have studied on the basis of our quantum number, which was known as subsidiary quantum number or azimuthal quantum number. Okay, and what this have told to us, that if we're representing L over here and it is 0, 1, 2, 3, 4, then we represent our atomic orbital S, P, D, F, and G. So now we need to discuss what are the shapes of these orbitals. Like what are the shape of S orbital, what is the shape of P orbital, what is the shape of D orbital. We have in your syllabus in 11th class only, we have up to only S, P, and D. That means we need to focus only and only about the shapes of atomic orbitals of these three orbitals rather than the F and G. Okay, so let's start with the shape of atomic orbital. First one about the S orbital. The S orbital are quite spherical in nature. They are spherical in shape, as well as they are symmetrical in all the directions. Now, it is quite obvious that if I'm talking that it is spherical in the shape, that means it must be symmetric in all the directions. That's quite obvious thing. Whenever I am putting that the shapes of S orbital is spherical, so spherical representing it is symmetrical in each and every direction. So the probability of finding an electron could be easier in S orbital rather than we are going to move in the P and G orbitals. Okay. So now before going to this, we need to study a term known as node or nodal surface. Now, from where this term arises, this is on the basis of psi square. I have told you that psi square is representing probability of finding an electron in an orbit. Okay, so whenever we need to study the probability in the psi square, and we have represented that in a graphical form with the equation, with the distance r. So we have some kind of graphs like this. where the r is representing the distance of that particular orbit from the nucleus. Okay, so this r is finally representing the distance of that particular orbit from the nucleus, and psi square is representing probability of finding an electron. So whenever we have taken this in the form of a graphical, we have observed that the psi square for 1s represents this way. That means the probability of finding an electron is maximum, but whenever the distance is going on to be increased, the probability reaches to a zero, reaches to minimum position. Okay, same as it is, this is for 1s. If I'm talking about 2s, it says that it goes to probability almost zero, then maximum to it, like this. Okay, so it is representing that first of all, the case is that probability is maximum, then it's going to decrease almost to minimum up to zero, and then it reaches to an height, a peak, and then it starts decreasing. Okay, so these kind of graphical representation which I'm showing to, that this is for 1s, this is for 2s, these things represent us a particular point, that whenever I'm talking about the orbital, the probability of finding no about 1s, 2s, 3s. From this observation, I can say when the probability of finding an electron also start decreasing. The reason is the size kept on increasing. I would repeat it again because this is very important. I'm saying that the size of s orbital increase with electron, sorry, increase with increase in m. Let me write this particular point. I'll come to notes again, but let me explain this particular topic. I'm saying that the size of orbital increases with increase in our principal quantum number n. Okay, so we can say that 4s size is much greater than 3s, then 2s, then 1s. Okay, and another observation from this point, we can say that the electrons are far located away from the nucleus. So we can say that the distance of orbital or electron that is present in that orbital also increases as n increases. This is quite obvious. Whenever I'm talking that there is 1s, then there is 2s, then there is 3s, the size is increasing as well as the distance from the nucleus also start increasing. Okay, because 1s, 2s, 3s, and 4s, this influences that the number of orbitals start increasing and they are getting far away from the nucleus. Okay, these observations we have observed by the experimental method which are given by these graphs. Okay, now I was talking about the node or nodal surface. What is the node or nodal surface and why do we need to study them? Let's start. Okay, what I was talking about that whenever we're talking about the node or the nodal surface, it actually means that the probability of finding an electron reach to zero, reach to minimum, that is known as node or nodal surface. So in short, I can say node is defined as that particular space, that particular area where the probability of finding an electron reaches to zero. That means we cannot find any kind of electron over there. This is a particular space, this is a particular area in our orbit where electron cannot be found at all, and that is known as node or nodal surface. Okay, so let's move to our next topic, that is known as I have given you idea about node or nodal surface. Now, how can we calculate the value for node or nodal surface? We can simply say it node also. The value of node is always equal to n minus 1. Okay, so if I'm talking about 1s, the 1s, there is no node over there. In 1s, there is no node. But if I'm talking about 2s, that means n equals to 2, there is one node present over there, which is over here. The probability is 0. Same as it is if I'm talking about 3s, 4s, and so on, the node starts increasing. Okay. All right. What else? Something else on this topic? I have given you all the idea about s orbital. That is it is spherical and symmetric in the nature. Second, whenever we start increasing with the quantum number n, like from 1s to 2s to 3s and to 4s, the size increase as well as the distance from the nucleus increase. And the third most important point is, as we are going to increase to our 2s or 3s, there is a kind of node, there is a kind of space where finding an electron is 0. Okay, and that is known as our node or nodal surface. All right, so this was the concept which we have derived from our topic, spherical shape of s orbital. Okay, these three observations were very important and give us all the idea, all the details about s orbital. Okay, now as we have completed our s orbital, I'm going to move our next topic, that is the shape of p orbitals. Okay, so let's start with the topic, what are the shapes of p orbitals. So let's start. Now class, you must have remembered that I have told you in our previous class that there is a quantum number known as ml. I hope you have remembered that. And ml was totally dependent on our atomic orbital L. Sorry, not atomic orbital, the quantum number L. I hope you have remembered this. है ना? तो उसमें हमने क्या पढ़ा था? That if I'm talking about L, that is if it is 0, we are representing S, 1, P, 2, D, 3, F, and so on. And besides this, we have studied that there is a quantum number ML, which is known as magnetic orbital quantum number. And it has given us the idea that it is totally dependent to, I should write it in this form, that its value is always from minus L to plus L. Okay, so if I'm talking about L equals to 0, the ML is only 0. That is, there is only one representation. Okay, same as it is if I'm talking about ML equals to 1, sorry, L equals to 1, ML equals to minus 1, 0, plus 1. That is 3 representation for p orbital. Why I have inserted this topic over here? The reason is orbital. In this topic, we will study okay. So up you will get why we have studied these quantum numbers. What is the importance of these quantum numbers? बन रही है जी बात? Basically, since ML proceeds of p orbitals, that is px, py, and p Now it's a little bit uh, tricky to understand that we here are representing our p orbital in 3 dimensions. The s orbital were only spherical in nature. Suppose this is our 1s, this is our 2s because yes, it is bigger in size. But the p orbitals, they are 3 dimensional in nature. First point, and second important point, they are not spherical in nature. They are not spherical in nature. Remember this point. In fact, px have two different sections known as lobes. Okay, so px, py, and pz, it has two different lobes. It has two different sections, and we also call them that it is behaving like a dumbbell shape. Okay, the dumbbell you have seen or you have used, I think, in the gym also. The dumbbell, which is of a shape that in the medium it is zero, it is nothing, and in the two side we have two different lobes, two different sphericals. Okay, same as it is, our p orbital are of dumbbell shape. Okay, the dumbbell we use in gym, that particular shape. Now we will see how it represents our shape. But before this, I have told you that there so this is something. Direction. This is suppose our y direction. There is nothing within this topic because we are talking only about px. Now, this particular point where these two lobes meet, there is also a node. Okay, where the two lobes meet in px, there is also a node, and the node represents what? Where is the probability of finding an electron is zero. It is nothing. We cannot find our electron over there. Okay, so this is our px, and this representation where the two lobes meet, it is known as node or nodal surface. Okay, Ji. Now, same as it is, if I'm talking about our py and pz, this is px, and if I'm representing py, it could be like this. This is our x-axis, this is our z-axis, and this is our y-axis. So this is represented in the y-axis, px, py, and same as it is, you can put our pz. I don't have space, so we need to rub this. And this is my pz. Okay, Ji. This is z direction, x, y. So this is pz. बन रही है बात? So basically, what I have discussed till now, that in p orbital, we have 3 different representation, and this is due to our ML, because ML represents 3 directions, sorry, 3 representation. Okay. So, and besides this, since we are representing our p orbital in 3 directions, so we have px, py, and pz, 3 different orbits with 3 different representation. This is in x direction, this is in y direction, this is in z direction. Okay, and its shape is known as dumbbell shape, and it has no spherical shape. It has 2 different lobes, and where they meet, that is known as our node. Okay, now same as it is, as we have discovered in our s orbitals, that with the increase in quantum number, the size kept on increasing. In the very same manner, we can say the size of our p orbital start increasing with the increasing quantum number. So keep that in your mind. Should say that the 4p is much greater than 3p than 2p. Okay, we do not have 1p, and why is it so? We will see in our next topic that why do we not have 1p. Why do we start our P with only from second orbital? Sorry, with the second quantum number, n equals to 2. Okay, we will. But I want to say that as the size increase, the energy also start increasing. That means they are far away, but their energy is also much higher than the 2p orbital. Okay, so these represent the energy as well as the size of our p orbitals with the shape. Okay, ji? So this was all about the shapes of p orbitals. Now let's move to our next topic, that is the shape of d orbital. A dumbbell shape in which two different lobes have meet. Okay. Sir, is everything okay? Okay, so let's start the shapes of d orbitals. I was talking about the shapes of d orbital, that in our d orbital, it is of double dumbbell shape. In p orbital, there was only two lobes which were meeting at a particular point. But if I'm talking about our d orbital, there are four different lobes which are meeting at a particular point. Okay, and we have five different types: dxy, dyz, dzx, dx square minus square, and dz square. These are our five representation which represents our d orbit and their shape. Okay, so now let's start. We briefly represent are these orbitals. Let's start with the d. Same as it is, I have told you that there is four different orbitals and they are representing at a particular point, at a particular lobe. This is known as something which is known as dxy, where this is x, this is y, and this is z. This is our dxy. Now, if I have to represent dyz, what would happen? The dyz would be in this shape. This is our z, this is our y, and this is our x. This is dyz. This is dxy. Same as it is if I'm talking about dxz, what would happen? Okay, x and z. This is representing as dxz. This is y. Okay. Now, what is the difference between dx square minus y square and dz square? The shapes of dx square minus y square and dz square are totally different. Love this. Okay, d x square minus y square and dz square. So if I'm representing dx square minus y square, suppose this is my x and this is my y and this is my z. So this is something which represents x square minus y square. Okay, I'm gonna rub this because this doesn't seem good. Now the shape doesn't much differentiate with the shape of xy, but dx square minus y square has some difference in the shape as well as in the orientation in mathematical way. Okay, so now it seems to be like this. We have already told this in our dxy, but in actual I haven't represented it well. Dx square minus y square is something around it. This is known as dz square. Now the shapes are quite different from all the 4 different orbitals, and how these shapes orbit and how these shapes of this particular orbitals have been changed. This is quite, higher from our syllabus. So it is beyond the scope. So now, right now, I just wanted to tell you that as we have studied the shapes of atomic orbitals, either I was talking about the s orbital, the p orbital, or the d orbital. In each case, I have described that in s orbital, there is spherical in nature as well as symmetrical in nature. The second point I have told you that in our s orbital, there is something that is the size kept on increasing with the increasing quantum number. And third point we have studied that there is a node or nodal surface where probability of finding an electron is 0. Okay, same as it is, we have studied with the p orbital, and I have told you that how do we come to know that there are 3 orbitals for p orbital, so 3 representation of p orbital, or 5 for d. This is on the basis of ml. -2, -1, 0, +1, +2, we have already studied in our previous classes. So these are our 5 representation for d orbital, and same as it is 3 representation of p orbital. So in the same observation, I can say with the increase in quantum number n, the size of orbital starts increasing. And secondly, what point I have said that there is a node, and the node is equal to n-1, where n represents quantum number. So if I'm representing 3p, there are 2 nodes. If I'm representing 4d, there are 3 nodes. Okay. Same as it is, there are some kind of angular nodes also, but that is also a very little higher topic. So we won't study this particular topic in this class. So this was all about the shapes of s, p, and d orbital. यहाँ तक I hope you have gotten the idea that अभी तक जो हमने study किया था in Bohr's orbital or we can say the other 4 model, that our orbitals are spherical in nature. That is totally wrong. Our orbitals have different type of shapes. So जो वो concept आपकी mind में था कि ये nucleus है और ऐसे orbitals हैं उसके चारों तरफ, that is not actual the representation. The representation in 3 dimension for s, p, and d orbitals. Okay, and that is different for each orbital. All right, this was all about the shapes of atomic orbitals. Now we will start with our next topic, that is filling of orbitals in an atom and the energies of orbitals. We have just discussed Now we will start with energies of orbitals. I'll just give a brief idea as we haven't much time left. Okay, the energies of orbitals. Right now we have discussed that there are 1s, 2s, 3s, 1p, 2p, 3p, so many orbitals. Now, how are they differentiate on the basis of energy? That is our next topic. So first, I'll just give a brief idea that on the basis of quantum number, we have studied that their size and their energies are increasing with the increase in quantum number n. So that is our first point. There are 4 to 5 different points which are based that how can we exclude or how can we differentiate our energies of different orbitals. And that is very quite important topic that we will study in our next class. So this was all by my side. Now, if you tell me if there is any kind of doubt or something in this particular topic. We have